KPM and advanced controls here at KPM. Professor Farid insights into building and transforming disruptive programs, especially in areas like artificial intelligence, twins, and Industry 4.0 will be very useful. Please join me in giving a warm welcome to Professor Farid.
Thank you so much. Thank you. It's a pleasure to be here. I'd like to first thank Dr. Mujahid for his kind invitation for me to come here. And your colleagues have been very, especially Dr. Sami just fed me a lot of fish. With the jet lag I have, I slept 2 hours last night, so this, he said that is the energy you need to go, but the blood is coming to my stomach. But anyway, it's a pleasure. It's an honor to be here. I love the culture and it's. I would like to share some of my work with you. I had one big presentation, one presentation prepared mainly on research and some mechatronics, but after meeting the colleagues here, I realized that I have to reverse the order. So this research presentation, I'm going to go through it very fast in the interest of mechatronics. So I'm going to pick some topics of interest. And because Dr. Mujahid told me that a lot of people may have come here from mechanical engineering, and that's my background, I would love to share some of mechanical engineering work in the beginning. So the other way. Oh, okay, fine. So in this presentation, I provide some introduction about me. I will talk about some of the key research areas. I divided it into two parts. My activities in Waterloo were very different from activities in Simon Fraser because of the nature of industry in town. I work a lot with industry. So that has, you see the difference. You see the difference. So this is a presentation. First slide is a presentation I gave to Simon Fraser University in 2006. That's why it says, it talks about Waterloo this way. But mechatronics has not changed idea-wise. So it still includes sensors, actuator, control. But what is missing is computer science. So in old days, computer science was not as important. It was like electronics combined with mechanical engineering and do control. But now everything is computer-controlled embedded systems. So if I were to regenerate this slide, I have computer science in there. One of my main, one of my main accomplishments that I'm very proud of is writing this book, Automatic Control System. This was an original book by Professor Benjamin Koo, who passed away in 2012. And I had the honor of being connected with him by Prentice Hall initially that established this collaboration. The 8th edition of this book is particularly very special to me because the day I had to submit the manuscript with Benjamin Koo to Prentice Hall, I should have written it as Pearson because they changed name at that time. Pearson was Monday, September 9, 2001. And my daughter was born that day. So 7 o'clock Sunday, September 8th, we had 3 pages left of the book. Benjamin Koo and I were on the phone. He's telling me what to do. I'm telling him, no, we're having this argument. All of a sudden, my wife comes in, says, I have to go to the hospital. And then I told that to Benjamin. He says, Farid, I have $3. It's most likely false alarm. Tell her. She can wait for a few hours. So I made that mistake that has never been forgiven. But I associate this book with my daughter. So it's very special to me. And then it has continued. 2007, moved to John Wiley because Prentice Hall became Pearson. So they had to get rid of me. But I abandoned John Wiley, and now I work with McGraw-Hill, one of the best publishers. And the next generation will come up in 2027. There is a big gap here, is because I was a director of the school and had a lot of administration load. So now I'm having time to do it. That's the next new one. And I also had another book that had to do with statics. And in Waterloo, I started my career in 1988, and because of the philosophies of University of Waterloo having to do with entrepreneurship, I really enjoyed it. So in Waterloo, I had two companies. First company started in 1991, 3 years after I joined. The focus of that company, Control Advancement, which we sold at year 2000, was products for visually impaired. Mainly haptic systems, basically force control, you feel the screen and you know where you are. But most importantly, with this MechWorks Systems Inc., the focus was on developing sensors for application of vibration control. So overall, in Waterloo, my focus was on vibration control applied to buildings, transportation system, trucks, cars, in general vehicles, but I also worked with Bombardier Aerospace on vibration reduction of propeller engines. And I did some work in medical application. I developed a watch, looked like a watch, this was in the 90s, that reduces the tremor associated with Parkinson's disease. Let me share with you the type of work I used to do. Anything that shook, I could control it. So, and I worked with key companies like GM, General Kinetics, L3 Communications, Pulsar, CRC, and Lord Corporation. Lord Corporation is one of the best companies to work with. They developed the magnetorheological fluids that now is inside dampers that they use in active, semi-active vibration control. So these are the type of works I did. It developed engine mounts, developed shock absorbers for isolating truck from the road, driver from the truck, and truck from the road. These are the list of companies I worked with, area of application. This is something I'm very proud of. This project involved developing active suspension for cattle. We were sponsored by GM. I had a startup company that worked with them, and we partnered with another company called Polymer Technology. They were into polymers and helping us with developing dampers, etc. And this is an old movie. This is a 2004 research, right? So don't forget, this is 21 years ago. This is a problem. Oopsie. This is a problem we wanted to address to minimize this type of issues and also address providing ride and comfort, road handling, and improve safety at low cost. Much better than existing passive technologies through embedded software. Now again, this is 21 years. So the solution was building our own sensors, attach it to the dampers in the car, and improve the performance. This is the frequency response of relative displacement and acceleration. So that was a problem. So to do so from year 2000 to 2004, we developed various sensors. Now, right now, sensors a lot of them are taken for granted. People go buy a $20 accelerometer or IMU, you put it in, they have built-in Kalman filters to reduce the noise and drift, etc., etc. None of that exists. So this is pioneering work, in my opinion, because we not only developed hermetically sealed accelerometers, but also we developed gyroscopes. This was the size. Now it's in a chip, but nobody addressed. They knew how to do address the issues of drift and noise, and we did a lot of work with Kalman filters, AI. Now you call it AI. I used to call it neural net then. To develop the IMU, we're looking at as positioning device for tracking motion. We did accelerometer-based IMUs. We tested it in my students' cars, and so that's kind of work I did. But let's go to other work we did. We did a lot of work developing dampers, solenoid valve dampers, Volvo, MR valve dampers, GM, Lord Corporation. We had the test facility to characterize these dampers. This one exploded once, and my little rheological fluids are made of iron particles. The whole space was black. It took a while to clean it up. And of course, we called it the universal Waterloo damper that we used for a company called General Kinetics for General Dynamics military vehicles suspension system. But in this case, we used the we used the MagnaRide damper built by GM with the help of Lord Corporation that I work with. So the idea was we put this through different frequencies and characterize the performance. Highly nonlinear system. As you know, in control system, you use DC motors because they're linear. So the control of something using this highly nonlinear system, at the time we only consider using neural networks with fuzzy logic to do that. So once you characterize the damper and develop, backwards. So we developed the sensors. We took one of our graduates to this car and equipped it with these accelerometers, took it to the road and collected data and fed it to a simple model. Then, and with that model, the goal was we want to do control on the software. Once we were comfortable with this, we got a Cadillac. GM didn't buy it for us. We did it ourselves. We leased the Cadillac, and we used the commercial damper they had developed, characterized it. We equipped the car with our sensors, and then we took it to a partner company to test it on a 4-post shaker. A 4-post shaker, as you can see, can simulate road conditions with known road conditions that it can use to train our neural network and also fine-tune our mathematical model. You see, they're going to see the different vibrations happening. You see? Good. So different type excitations was done. This was done in 2005. Then we used a program called Adams at the time to simulate, once you have the model established, to simulate the vehicle, apply our controller to it, and compare the performance. No control, just normal suspension, you see, and with suspension, with our active suspension. So once we were comfortable about our control system using Adams software, we can watch this close up. So it goes through a bump, you see, uncontrolled, active control, semi-active control. And the control is done by adjusting the valve to putting the under a magnetic field, right? And adjusting the magnetic field, you create a valve. And that's how you do control. And then we took it. This is December 9th and 10th, 2006. Exactly 2 years. Took it University of Waterloo, of course, snow, uncontrolled. See that? There's a laptop there. Everything goes to the laptop. Laptop including the control. Very much different. So it matched exactly the advancement. It's another thing for Golnaraghi, you have to do a double lane change. They do the 100 kilometers, the police didn't let us exceed 50 kilometers. You may not have seen the difference, but you could hear the squeaking, and the time response clearly shows the difference and success of the technology. I did a lot of work on condition monitoring. I'm not going to spend too much time on this. I'm going to just go very fast. I work on printing presses. Printing presses, if there is a damage to the gears or the damage to the bearings, there is a doubling problem. Sometimes when you read a newspaper, the color are off. It's because of these problems. So what we did was, that's inside the printing press, 3 stories. So we equipped the different around the rollers with accelerometers throughout, and we had our neural net running. We established a clean system, healthy system signature, and through that we could find what was going on, right? So if this bearing, for example, is shot, the operators have a hard time finding it. They do it by hand. They sense the temperature, and then once they find it after a few hours, then they have to take this roller out, replace it with a new one, or fix it. So we use a neural net system, collected data, and we were able to identify local phenomena. That's me. Yes. The fumes of ink is very. So I also worked on controlling vibrations of Taipei tower, using a model of it and adding active control. They didn't buy that because they were scared of active technology, so they put in a big pendulum in there. Very, very beautiful. It's a tourist attraction. But I worked with another company doing that. I also was involved in developing active elastomers by putting iron particles inside elastomers and cure it in a magnetic field. And then once they are aligned under magnetic field, you can get a change in stiffness. And that's where you can do control, normally for engine vibration. Yeah, so that was a sample Waterloo work. Now we enter SFU. SFU is in Vancouver. There's no automotive industry there. Everything relies around or revolves around medical applications and startups, and so I was gravitated toward medical side of things, where we developed a near infrared probe that I briefly will talk about, that is used to diagnose breast cancer. I've been working on that since 2010, and now have successfully tested 137 participants at BC Cancer with the goal of detecting tumor in the breast and response of the tumor to chemotherapy. I do also work on, I have developed a new MEMS gyro with my colleague, nonlinear gyro. And I have also, that's another leading research I'm doing to make helmets safer for concussion. I'll briefly talk about that. But also I'm working on EEG research using nonlinear dynamics, phenomena, chaos theory, etc., to do signal processing. The goal was to do concussion detection, but I found it to be very difficult because how many people you can find that have concussion and are willing to come for tests. Right? So I applied this idea to detecting drowsiness in mining truck drivers, because if they fall asleep, those big trucks have an accident, millions of dollars is out. So I talked briefly about all this. Briefly, this is really highlight of my work. I'm very proud of this research, where we use a near infrared ELEDs with 4 wavelengths. There are four wavelengths here, 4 wavelengths here. These 4 wavelengths are tuned to absorbance of 4 constituents in breast: fat, water, oxy, and deoxyhemoglobin. Tumors need blood to grow. They need lots of blood to grow. So that's our marker for identifying tumors. So when you place this on tissue, this diode first sends 4 wavelengths consecutively, and the light is going in. Some of the light is absorbed, some of the light is scattered. The back scattered light is collected by the CCD array, 4096 pixels. Then this one turns on, and then we do the same. This way, we add to our confidence level. And what's going to happen is, so far we spent more than $1.2 million developing it. The highlight of our work is we, in 2022, won an award from Canadian Space Agency for one of the top 20 innovative technologies in Canada for technologies for space and remote areas. And then BC Cancer also recognized us for this technology. They're very active in research. We work closely with them. So let me show you how the technology works. We use phantoms. Phantoms, in this case, is a Delrin phantom. Delrin is a material that mimics fat closely. So what we do is we insert a hole in here and fill it with iron. Iron has properties similar to blood, so it is a good way of measuring anomalies. So we go on top of this, we do the different measurements. So we send light, we collect it, and as you pass through the anomaly, you can see, well, by the way, this is based on theory of light using Beer-Lambert bulb. You see it's very noisy. We use AI, we use neural nets, CNN, to make it cleaner. And it's so fast, the accomplishment, this is real time. So you see these anomalies changing in real time. So your perspective changes as you move the probe. So we can identify the anomalies. We can actually identify the size very closely. This is depth. We can also measure the depth and this move. And then we had patients tested BC Cancer, and this shape has to do with the light travel. It's very similar to ultrasound, right? So that's why we don't fill the whole square. But basically, using our imaging algorithm, we could identify the anomalies in patients. We could generate an offline 3D image that matched perfectly with the ultrasound. And furthermore, we could identify dimensions, depth, and width, and that matched very closely with ultrasound. And apply to all of them, right? So we could characterize the tumor. With that said, we can do different measurements as slices. So we covering the whole area, then we can track the size of the tumor in 3D. And this is the type of slices images you see. You see, as you go through the slices, you can see. You see, you can see the tumor. And here, there was another tumor here. And then using 3D models, we can see how the tumor is shrinking, responding to chemotherapy. So this is where we are right now with this work. 2 weeks ago, we started the company to spin off the technology. And the idea is take it forward as much as we can, get FDA approvals, and then work with a company like Siemens or Philips or who has money to take it further forward in the right direction. This technology also applies to, we have applied it to vascular issues. We have applied to fatty liver, kidneys, and rheumatoid arthritis. You can detect inflammation. So basically, based on the absorbance theory of light, we can tell what was there to absorb this light. Is it inflammation? Another work I very fast talk about it. We have made helmets safer for participants in sports, construction. Concussion brain injury does not happen often when you have a direct impact. A lot of times it happens because of sudden twisting of the head, right, like this. So now if you're wearing a helmet, this helmet is tightly attached to your head. When you have a side impact, your head goes with the helmet. Brain inside the skull stays behind. The skull turns, and the brain, the tissue in between turns off, causes hemorrhage and concussion. Right? So if you want to improve the helmet performance, you better work with friction to eliminate friction or reduce the friction between helmet and the head. So when the impact occurs, the helmet turns, your head doesn't. Right? So that's the idea. I'll show you. It applies to many areas: occupational safety, construction. We had independent testing of. This is not our product, but this is just a picture. We have tested it at Virginia Tech, and we received one of the top scores that they have. So the idea is we use fabrics, multi-layer, nanomaterial, and some lubrication in between that allows this fabric, when you have an impact, to absorb energy while it's sliding, disengaging from the head, and then when it bottoms out, the head goes. Let me show you an image or a video. This is with football helmets. You see the difference. They're both dropped after impact. Without our technology, the rotation of that one is much smaller. So it disengages and reduces chance of concussion. This is that's mechanical engineering, right? Oh, I have this too. I also work on these. One of the main reasons the price of honey, at least in North America, is going up is because bees are getting these mites that essentially eats them up and kills them. Right? So the farmers, and one of our specialties at Simon Fraser is called agri-tech. So some of us do work with agricultural companies or farmers. We equip a hive with our sensors and monitor the crowd from temperature, movement, etc. So if the hive gets sick, the movement reduces, temperature goes down, the farmer has to go attend to it. And the way they get rid of these mites, they put them in containers full of icing sugar. And they shake it, the mites come off. It's very low technology, right? So that's what I did. So that's the end of this conversation. So I'm now gonna move on to Mechatronics. Thank you. Oh, yes. Thank you so much. Okay, so the second phase is what I really should have been talking about, and I get excited about my research. So this is what I did over since 1998 in the area of mechatronics. So I talked about my research. Again, I'm going to talk about mechatronics at Waterloo briefly, but more focus on Simon Fraser University. And also I want to highlight some of our achievements, namely having to do with Siemens Mechatronics program, certification program. So that's how long I was in Waterloo. This is SFU. I had a Canada research chair there. I became a fellow of CSME, and I moved to SFU as a director to start the school. I ended my term there. It was a very long term, right? And it was I don't recommend it to anyone, especially you. It really affects you because you deal with a lot of problems all the time, and that's why that book was not written as fast as it should. So anyway, this is a messy slide, but I had to show you to demonstrate the red is my journey, mechatronics journey. Okay? I started as a mechanical engineer and went to theoretical and applied mechanics. I spent 6 years doing my PhD because I wanted to learn as much theory as I could. And frankly, I raced too fast. I missed a lot of stuff. Right? So, but what I was trained in was control theory, whereas here it was more in dynamics. And this is what I got into vibrations through my PhD, controlling of large space structures. Then I moved to Waterloo, and let me share you with the other slide. I went to Waterloo, and I was the only person teaching control systems, but 8 years later, with my group, we lobbied the university so much they finally said, okay, go ahead, start something. So we started a mechatronics option. It was a failure. And the reason it was a failure was collaboration among 3 departments. Each department was teaching their own courses to students from outside department, and 30% of our students failed. Every electrical engineering course, they took 30% because the electrical engineering people were teaching course to their own students. And if you're in the 4th year mechanical engineering, you don't want to know about circuits. You really don't. You don't understand. And electrical engineers, they don't want to know about gears. Right? So that's a major difference. So the idea was, how do we fix the problem? To fix the problem, I started 3 biannual workshops on mechatronics, which led to developing a dedicated mechatronics program at Waterloo, 2003. These workshops had one conclusion, and that conclusion is very important if you're trying to establish a mechatronics program, that mechatronics, just like mechanical engineering or electrical engineering, is a culture. And you need to nurture it, what it deserves, and develop courses for it, not use electrical engineering courses to teach mechatronics students and mechanical engineering. It has to be developed to create a new degree programs combining all the necessary items. The key item is design, not mechanical design, overall design. integrated design. All right. Now, of course, you need computer control. But that was a message we got from these events. We had experts from all over US and Canada coming in, share their thoughts with us. So that we needed this message to convince the university to allocate resources to be able to do this, and they did. We hired 22 faculty members, distributed amongst the departments, but all share the same philosophy, right? We are all mechatronics, not systems, not electrical, not mechanical. We also changed the department name from mechanical engineering to mechanical and mechatronics engineering. So we have 2 degree programs within there, 5-year mandatory, five-year program, but 5 co-op terms as well. And first intake was 100 students. Basically, I don't want to put more time into this because I want to go to the SFU one, but this was the curriculum, 132 credit hours, combining, mechatronic sensors, actuators with electrical, with mechanical, and that was the end of that. But these events led to SFU contacting me, asking me to join them to start their mechatronics program, which I did. Partly also because my wife is from Vancouver, so we needed to move to Vancouver. So, and that was a right opportunity for me to move from Waterloo to Vancouver. And because of that, again, the university committed to 21 faculty members, now beginning 22. There's a serious budget issues right now in Canada. So we should have been 27, but we're good. 600 undergraduate students, 120 mainly PhD students, and the faculty focus on these areas: biomechatronics, energy systems, MEMS and nanotechnologies, mechanical, mechatronics design, and intelligent mechatronic systems in general. But here's my key activity as a director. Started the program in 2006. I developed the curriculum. The difference with Waterloo and SFU at the time was I added a lot of entrepreneurship in there because of my personal experience, because of my training at Waterloo. And with that exercise, I created a double degree program with the School of Business, a 5-year program that mechatronics students can become managers of tomorrow. But also we got funding from donors that created a Tech E program where E stands for entrepreneurship, and we use the money to pay students to run their own company. But we provide them also with mentorship and support, bring engineering students to business students, to engineering students, establish that culture of working together. Don't say I'm an engineer, I know everything. We need business people to run the show. That's a simple fact, right? Engineers running a company 95% of the time fail. Because we as engineers have a hard time talking to people. We talk to the computer much easier. So we need business people. But that culture has to establish. So it did. And I also focus a lot on technical and business writing because engineers, at least in Canada, don't know how to write. So we critique them, we emphasize on that. So anyway, I will talk about this too because 2022, I championed a new mechatronics program with much more innovation in it. And I'd like to share that with you. That was the really scary curriculum I created. I look at it now and say, why, right? It was 146 credits, 6 courses a semester, and no break, really. And the problem with that was student took, instead of 4 years, 5.3 years to finish. But they left happy. I'm telling you because we still have good job market for them, but one of the companies that we closely work with, and in 2012, I went to them, I pitched for Mechatronics, and they came up to Canada and started hiring our students. After 3-4 years, they told me, you need to train them better. You need to train them to be more hands-on. And then they introduced us to Siemens program that I will talk about. So we needed to make a change. We need to relax the program a little bit, reduce the number of courses. Let me highlight it. 3 mandatory core terms, focus, as I said, on entrepreneurship, but there's no room for innovation. The program is full of courses. There's no room to maneuver. So and it was light on computer software. So we have to deal with the issues of how much sacrifice we have to make on fundamentals versus the more engineering type courses. Each university has their own culture. Our university, Simon Fraser, is not an engineering school. So the philosophies are different than what Waterloo was. But so the reason is, so we had to tune it with their vision as well. So we did. And we need resources always for a new program. We had to convince them to help us out. And after all that, they have to find jobs. So we have to help them in that area. How much time do I have?
Yeah.
2 minutes?
10.
Oh gosh, okay, I better hurry up. But the key goal was reduce the number of courses to 132 to reduce graduating time, provide hands-on experience relevant to industry. These were our goals. It took 6 months. Yeah, it took 6 months to do the research. I missed the slide. Yeah, it took 6 months to do the research. We got feedback from the industry. We reviewed our competition. We reviewed the Canadian universities that offered mechatronics because we are competing with them. And also because I can proudly say we have better mechatronics programs than the United States. There are now only maybe 1 or 2 mechatronics programs in the US, but I can assure you they copy us. I mean it. In Carnegie Mellon, one professor that was supposed to come to us ended up there, and that's why they had mechatronics. So I believe that. But anyway, so we achieved this by bringing a lot of changes to our first 2 years. We introduced hands-on training through design studio courses, hands-on courses. Students, instructor walks in, this is just a lab, like a lab, but they build things and they interact. So it's more hands-on. We introduced PLCs early on, year 2. That's very important. Industry wants PLC training early on. We were offering it rarely in 4th year. Introduced PCB manufacturing and machining, and these are all hands-on training. How to solder. Surprisingly, my students in 3rd year, 4th year had difficulty soldering. And so we teach them all that. We added more software training, and that's our curriculum. So I will elaborate very fast. 132 credits. Notice there's no break. So if it's a 4-year program, fall, spring, summer. Fall, spring, summer, they go to fall. So it's a 4 solid years still. Mechatronics is very demanding still. But what we accomplished was we have significantly improved our computer hardware and software offering. Particularly in 1st year, we teach them C++ in 152. We teach them digital computing fundamentals, advanced topics in C, so another programming. And in 112, we teach them Python, but embedded programming. So we introduced them to embedded systems year 1. even before they start taking electric circuits and all those engineering courses. Digital logic, real-time embedded control system. So we added significant computer software, hardware in our program, significant mechanical engineering. Focus is we took over physics 1, offered it ourselves as statics and dynamics of particles, and then Mechanical Studio 2 does 3D printing. Teach them how to 3D print CAD, design concepts, is project-based. So the standard strength of material, these are skeletons of mechanical engineering, right? Okay, and then design is also, but machine design very important because you work with gears and when you have motors, so it's important to know how to design mechanical systems, fluid mechanics, thermodynamics, and heat transfer. Also, we have significant electrical engineering content, control systems, real-time embedded, a lot of focus on embedded systems as well. But one thing we did was take over some of the key courses. Statics was replaced with, the physics was replaced with this course, particle dynamics and statics. Statistics was replaced with engineering, measurement, and data analysis. We teach statistics through experiments. This is a course I'll be first time teaching in 1 week. I replaced differential equations with a course called Modeling of Mechatronic Systems. I would love to talk to you briefly about it. And we have introduced the Siemens Mechatronics certificate program that brings really hands-on training for our students. This is a course I'm about to teach by means of experiments. It's heavy on labs, where I teach differential equations using labs. Anybody who's taking differential equations from math departments as engineers will agree that you had a hard time understanding why we need differential equations. So now I start with this second order system. I pull it, let it go, and I solve it. And then they realize, the models that they develop actually matches the experiment. There's friction in here that the differential equation doesn't teach. So I talk about that. And we built our own setup, designed by our students, built by our technologists. And now I'm looking at this, I say, well, this is 10 times better than Quanser's system. This costs $750 each. Quanser similar system, $20,000. It's no brainer, right? But I cover everything, the differential equation, Laplace transform. So that is, I'll let you know in a few weeks how I did. Lab-based, 40% lab. The students come in, they do mass spring damper. We have RC circuits, RCL circuits, and we do analogies and numerical simulation, etc. I'm almost done. This is my course too. This is a capstone, very important in mechatronics. The goal of it is to bring everything you have learned into one course, design and build something. There are 3 classes of projects: industry-led, faculty-led, or student-led. All treated the same. And the students come in, they pick either a proposal, a subject from industry or from a faculty member or their own idea. I'll teach them, well, they write a proposal without any knowledge of how to write proposal. Then I give them a lot of hard time, say, well, you have to do it this way. First, you have to generate the functional requirements of the system you have. There are government regulations, there are standards that you have to follow. There's a budget that you have, all that create the space that you have to operate within. Once you do that, then you can come up with 10 designs, pick three. Pick three and use the specification to find out which one is best. Then we use the concept of known as design matrix, that we choose the right design, and then they present the design, and next term they build it. Once you build the design, that you have to write a user manual, a complete one to address safety, features, how to operate, troubleshooting, everything done professionally. Because if you don't present your design properly, you could get sued, or nobody would buy your system if they have a hard time running it, right? And every year we get 1 or 2 startup companies from students. And every 3 years, one of them hits it very big. So that has been a very good success story. So basically, can I? Siemens program, I shut up. So basically, yeah, this is introduction by Tesla. We managed to get this program in place. Certified professional engineers and our students. I sent 3 of our professors to Germany to be trained on level 1, 2, and 3 of Mechatronics program. Basically mimicking a factory and with various elements of the factory. It has 3 levels: hands-on training, learning about PLCs, electrical components, and all the way leading all the way to more complicated stuff. As I said, you need to have minimum of 2 faculty members trained by Siemens or us. We are the only university in the world that does this training, recognized by Siemens. That we are on their website, right? We even teach the instructor. We are the only university teaching the instructor. Taha Al-Khudairi, Mohammed Narimani, and Amir Marzouk are the 3 instructors. They have spent 3 years in Germany learning about how to train instructors. And then follow up after I left as a director, they continued it with smart manufacturing professional masters. All right, so I'm almost done. We have 3 labs in this smart manufacturing hub, industrial Internet of Things, and digital twin lab. With a highlight of using the VR headsets to simulate factory environment, and this is amazing. Yeah, I'm done. Those are some thoughts, but I can. Sorry for the rush, but I had to cover everything there. Very nice. Thank you. Yes, please.
Yeah, thank you very much.
My pleasure.
Really appreciate it, John. I just wanted to commend you on your Waterloo Mechatronics team.
Oh, thank you so much.
I used to be a motion sensor manager at Apple, and Waterloo Mechatronics graduates were our best hires.
But SFUs are better now. I know
Yeah,
that.
I'm sure they are. I'm sure they are.
Thank you, thank you.
My one comment would be that they were very good at getting in and getting the interview, and they're very hands-on. They missed a little bit when it would come to rigor and fundamental understanding, but they were very hands-on.
Yeah, I agree. I agree. One thing, I 100% agree with that aspect because fundamentals were not as strong in Waterloo. But we teach, even when I teach our own differential equation course, we stress a lot on fundamentals because of my own background. I can do many different research because the basis I have covered, right? So thank you for that comment. I agree with that. Thank you. Yes, please.
Which programming language you would teach for PLCs, like ladder logic, functional block? Because I've heard that ladder logic.
I don't know. You see, one thing about me is I'm not expert in any area. And mechatronics is a field that you have to do teamwork, but I don't know the PLCs that well. But the people that I hire, they know it very well, so I can connect you with them and they'll help. If you send me an email. Is it possible? Thank you very much.
Thank you so much for that.
My pleasure.
Yes, one question is, I have seen where the tumor detection technology has gotten to. But didn't tell us after the root test of the University of Waterloo, where is it currently?
Sorry, I don't understand the end of the.
Yeah, as in the Waterloo damper that you created.
Oh, that's the one damper, yeah?
Yes, yes. That tested it on the road, but after that, what happened? Has it got into industry? Where is it?
So the damper we created, yes, it went to, we worked with a company called General Kinetics, which essentially supplied components and parts to a company called General Dynamics. General Dynamics is an American company, but they have a branch in Western, is in London, Ontario. They built these six-wheel vehicles that carry soldiers, right? Yes, for them. We built a prototype. General Kinetics made it a professional product and used it. So that was done. With GM, we decided to use their already made professional system. So why reinvent the wheel? We just made it work better. Thank you very much. That was a great question. Yes, sir.
Regarding the PLC programming, your instructor working on the Siemens only, but
No.
in different industries, there are different PLCs in the different.
No, I know.
Maybe the student who graduated from your institute, he or she has only hands-on experience from the Siemens, like S7, S7, S7.
No. One thing thank you. That's a good question. Let me elaborate. The Siemens program. That's why I missed the final slide. Let me bring it back. Perfect. Never mind. No, it doesn't matter. The Siemens program in our university still optional. Most people take it in their final year to get the ultimate hands-on experience, but also the certificate that they can put on the CV to get the job. But in the second year, Amr Marzouk uses different kind of PLCs. But again, I can connect you to them, or I can email Dr. Mujahid what they do in first year and second. So, but the point is very valid.
Like as the technology become smaller and smaller day by day, how much time it take for the microcontrollers like STM32 and these segments to be more computationally powerful so they can run neural networks like the machine learning algorithm directly? What are the challenges right now?
I don't know the challenges right now, but I can share you the challenges I had in 2006. The laptop you saw on the computer on the car was controlling the car. My student generated a MATLAB code that was 30,000 lines. In 2006, microcontrollers could take only maybe 20, 30 lines. So it was a huge challenge to adjust it to GM's technology. And that's something that I faced. At this point, I don't know the challenges beyond what I said.
You have a lot of programs in the whole 5 years of duration. So are you mastering only one program for first students, or every student will have to learn all the programs that you have mentioned?
Yeah, we have a core system, they have to learn it. They start in year one, we teach them the basics of the science, and yeah, they have to go through the whole program. And only final year, so we have, if they finish in 4 years, they have room in 5th year to specialize. That's where they take Siemens program. That's where they specialize in, for example, in energy systems, or they want to do design, they specialize in design. So only in the final 5th year, if they elect to stay to specialize, they do different.
I got a couple of questions on your 146 credit hour mechatronics program.
Well, that was a crazy one.
How come nobody objected to that?
Because SFU wanted Mechatronics so bad that when I went there, nobody challenged me.
I mean, how come you got away? Yeah,
Uh,
I don't think so. They would ever approve such a program.
no, well,
146,
we ran it for 17 years.
146 credit hour.
Yeah.
And I bet it was okay.
It was okay. SFU is tough with the engineering. Engineering science also had about 100 and maybe 40 credits.
Because I don't know, they don't allow more than 127 and 130.
Yeah, Canada is different.
Right.
That's why our mechatronics programs are more successful, because we teach more courses and provide more background to our students. Now, I'll be honest with you, mechatronics is, you cannot successfully do a mechatronics program with low credits. And those credits has to be, a lot of them has to be technology courses, right?
The other comment is just, you know what you're trying to do the next semester. We have done that many years ago. We did that on a vibration lab.
Yes. You shared that earlier.
You know, so we managed, we developed in-house
Yeah,
experimental setup against every chapter,
yeah.
against vibration and control.
That's fantastic.
Yeah, and that was the response we got was amazing.
Yeah, it is.
You know, some of the students, I'm not sure if he did it, but one undergraduate student, they just loved it.
Yeah, no, that's,
They get engrossed completely.
yeah. I love to share that with you in a few weeks. See how's the,
I can share you my experience.
yes, I would love
We
to.
got a manual as well developed for that.
Yes, please. We can talk more.
Yeah.
Yeah, I love it. Now, this is the way to teach engineering.
Usually something got problem with learning.
Yeah.
Yeah, and that was just amazing experience.
Yeah, no, I buy that a lot, because I've had students coming to my office and crying that so-and-so from math failed me. I don't know what they're talking about. So I had so much fight with math department that at least put somebody with engineering background teach us. So they did, and so we took over.
The kind of thing you're trying to develop, we built that.
Wonderful.
Vibration. I'm instrumented that everything.
I like to see that.
Yeah, I can.
Thank you. Yeah, that's good. We have a lot of time. Yes, please.
It's just a question. There seems to be an issue in engineering degrees in bridging the fundamentals and still prepare the students to handle the industry. Now, in engineering programs, they have to be established in a way that a large portion of the courses is from math, physics, and general studies. I can see that the approach that you follow here is somehow you hijack those courses.
Yes, no, we didn't hijack. We took them over because they rightfully belong to us. No, I agree.
So it is essential because let's say a student in an engineering degree will need to take at least 5 math courses.
Yes, we teach them all 5. We teach them 3 math courses, calculus 1 through 3, linear algebra, and differential equation. But so who teaches it? Differential equation, we teach it because my background is vibration. I know differential equations. I've gone to theoretical and applied mechanics. I know math better than a lot of mathematicians. Sorry, I don't want to arrogance.
This is an important issue. With 5 math courses, 2 physics, and chemistry, among some other basic courses. you don't have much room left.
Yeah, oh, yeah.
You saw our curriculum study.
Yes, I did see that. I see that.
Especially, yeah.
But I think this is gonna work, so I'm very proud of this.
Is there any other way other than fighting with the math and physics and this?
You know, it's a good question. Fight is not the way, and surprisingly, in universities, not here, but in North America, I see a lot of fights because this is my course. My course, I want to teach it for 20 years exactly the same way, right? So no, you have to work together. Times change, technology change, so teaching habits have to change. So right now, everybody uses iPhone, everything is moving very fast, and the attention span is low. You have to make the courses exciting and interesting for students to absorb it. That's the whole thing. Thank you for that question. I appreciate it.
Okay, maybe one last question is.
I just had a question on the LED-based
Yes,
breast cancer detection. I wanted to know how deep in the
5 centimeters.
5 centimeters.
Mm.
So is that good enough for most?
Absolutely.
So
In 137 patients, we tested because when people lie down, gravity adjusts things, and only one case we could not do.
you know how this would compare against? I used to work as a postdoc with Professor Kalervo Hoinen in Sunnybrook Research Institute, and he was working on focused ultrasound-based.
The ultrasound cannot detect. See, the difference with ultrasound and light-based technologies, like you can tell what material absorbed that wavelength better. Whereas with ultrasound, everything is the same. It shows things, but you cannot tell what it is. And that's where you need professionals to assess it properly. And yeah. Thank you.
Okay, thank you very much for.
Thank you very much.
Thank you very much.
Thank you.
Thank you.
I appreciate that. Sorry, I had to go very fast. I had to cover. Thank you. Thank you. I appreciate that. Thank you. What else? Yeah. You can copy my signature. It's like. It's very easy.